Welcome back. Hope everybody enjoyed their 3-day weekend. Maybe even for some of you it was science-free, but now we're back. So it's interesting, that we have this policy to start 5 after the hour. It's a lot of fun to watch the participants number. You're all conditioned to now come at 5 after the hour. Even though we've built in this grace period, you've caught on to us. Week 6 is How Does Gas Flow into Galaxies week. I guess we've decided over the years galaxies breathe in a way. They inhale and they exhale. Last week was exhalation, which tends to be spectacular. Inhalation is more subtle, and yet without it, galaxies couldn't exist. So this week, part of what we're trying to figure out is how that gas got into galaxies to begin with. It's the 6th week of our 8-week program. It's amazing how much I've learned in the last 5 weeks. And we have 3 more weeks to go. I think we're going to set a record for learning in an 8-week period from listening to all our speakers and panelists. Before we get to today's keynote talk, today our keynote speaker is Kate Rubin from San Diego State. And she has been a leader in how gas flows in and out of galaxies. She could have given a talk on both sides of the respiration process, but she's going to be talking to us about how gas flows into galaxies today. And we will have a panel discussion following her talk featuring Nicholas Later, Trika Vandervoort, Gwen Rudy, and Claude-André Fauché-Jaguir. So with that said, I want to yield the screen to Kate, who will introduce us to how gas flows into galaxies.
All right, thank you very much, Mark. First thing I have to say, this has been a phenomenal workshop. The organizers have done amazing work putting all of these activities together for us. And I have indeed felt inspired over the past 5 weeks in a way that I had not for quite a while before that. So thank you, organizers, very much. And I'm really happy to have this chance to talk a bit about the empirical or observational answers to the question, how does gas flow into galaxies? Now, one thing about speaking a bit later in the workshop is that your question gets answered by previous speakers. So it started all the way back in week 2 when Todd Tripp told us that, at least in the Milky Way, there's a lot of evidence that the gas that is flowing inward toward the Milky Way's disk is multi-phase. It's detected in H1 21 centimeter emission, but also in low ionization metal lines, intermediate ionization metal lines, and highly ionized metals like O6. So that's one thing to keep in mind as we move forward here. Then in week 4, Mary in her keynote talk impressed upon us the complexity of the morphology of gas flows toward the Milky Way's disk. So here she was talking about large complexes of high velocity clouds, which are composed of multiple clumps within these large complexes, and then are surrounded by a whole bunch of additional smaller clouds. And she also made the point that if you increase your spatial resolution, increase the spatial resolution of your observations, you're probably going to be finding some even smaller clouds. So that's another thing we should keep in mind as we move forward. And then finally, and then also in week 4, Filippo said that gas accretion occurs vertically over the disk and not at the edge of the disk. And here he was specifically objecting, I think, to this blue stream of accreting gas that's falling towards this galaxy along its major axis, and instead was arguing that gas is accreted primarily vertically toward galaxy disks, and that accretion is triggered by condensation. That condensation, is triggered by galactic fountain flows, and which trigger condensation of the hot coronal material. So my initial reaction when I saw this was, do we have two competing models for how gas flows into galaxies here? And I'm not quite sure that that's the case, but let's think about it a little bit more. So first of all, neither of these images show actual models. They're both schematics, but the image, the model that is evoked by the image on the left here was laid out in Marinacci et al. 2011. And perhaps has some similarities with the predictions of the simulations of Kim and Ostreicher, who are doing very detailed, high-resolution simulations of the interaction between star formation in the disk near the solar neighborhood in the Milky Way and the coronal material just above that. And one thing I find really intriguing about these simulations is that the sense of the velocity of the gas above the disk changes with time. Sometimes it's flowing away, sometimes it's falling back in. And so that has some similarities with the predictions of Marinacci, Fraternali et al. And I do hope we'll be able to hear more about the predictions of these simulations, either in the discussion today or on Thursday. Now, the image on the right here is also not a model, but it is perhaps meant to evoke the predictions of cosmological simulations, which have predicted for some time that large-scale flows of gas tend to accrete onto galaxies along their major axis. And this figure is just showing one such prediction that Dylan showed us last week. This is a figure by Sylvain Peru, and it's showing a map of the gas radial velocity around this galaxy at redshift 0.5 selected from the illustrious TNG simulation. And indeed, they're finding inflows tend to occur along the major axis, whereas outflows occur along the minor axis. So I don't know that these two models are competing. They certainly share many aspects. There is a recycling of gas in this diagram here. So this model is perhaps inclusive of the predictions of this model. And perhaps really the question is about how important major axis flow is relative to vertically directed flows. So in principle, we should be able to answer that question observationally. And really what we want to do is figure out what the inflow version of this function is. This is the function that Dylan said we need to measure to characterize outflows. This is the mass outflow rate as a function of distance from galaxies, as a function of azimuthal angle, or viewing angle, I should say, as a function of velocity of the gas, as a function of phase and metal content. So really, what we want to do, what we have to do, is characterize the mass inflow rate onto galaxies in the same way as a function of these same parameters. Of course, Dylan also brought in other parameters that I'm just going to totally ignore here. It's even more complicated than this. But this is our goal. We'll just leave it there. We want to measure the mass inflow rate as a function of these parameters. We're not going to be able to do it, but we're going to take some baby steps toward this goal in the talk today. And we're going to be able to make some progress first by looking at what we can learn from measuring abundances of H2 regions. Then we'll look at insights from studies of neutral hydrogen in 21 centimeter emission. And then finally, we'll take a look at insights from absorption line studies of galaxies. So, before I proceed, if anyone, I really don't mind answering questions as we go, so please feel free to shout it out. Maybe I'll pause a few times during the talk. All right, so let's start with these H2 region abundances. What can we learn from making this kind of measurement? So, we can make some progress if we have spatially resolved information about H2 region metal abundances. And we have that now thanks to the Sloan 4 MANGA survey, which has obtained quite deep IFU, integral field spectroscopy, of a sample of 10,000 nearby galaxies. And so Huang et al. Has taken advantage of this to identify regions in these galaxies which have anomalously low metallicities. So how they do this is they first have to establish the baseline relationship between local metallicity and stellar mass surface density in these galaxies. And so they demonstrate how that is done using this figure. So for instance, for all galaxies with a total stellar mass of 10 to the 10 to 10 to the 12 solar masses, they plot the metallicities they measure in every spaxel in those galaxies versus the stellar mass surface density in those same spaxels. And this pink ridge here shows the mode of that relationship. So that's where most of the galaxies, most of the spaxels in those galaxies lie. Then they identify regions which are significantly offset from that relationship. And up here in the top, they're showing us maps of that offset. So the color bar shows us this delta metallicity. So metallicity relative to this ridgeline here, normalized by the dispersion in the relationship. So objects or regions with very low values of this quantity have anomalously low metallicities. I have gotten better at saying that over the past day or so. It was hard at first. So in this galaxy, it has a lot of anomalous regions. They consider values less than -2 to be anomalously low. So this galaxy has quite a bit of area covered by that phenomenon. And in this other example here, a much smaller area of the galaxy is covered by these anomalous regions. They find overall that these occur in about 25% of all manga star-forming galaxies, and in about 10% of all star-forming spaxels in manga. And in a later study, they also constrain the nitrogen to oxygen ratio in these regions and find it suggestive of disk gas mixed with lower metallicity material. So their argument is that these anomalous regions are caused by intermittent inflow events of lower metallicity material. They can measure the approximate stellar age in these regions, also using the manga data. They find that the stars in these regions tend to be about 250 million years old. And so if you treat this 25% occurrence rate as an indication of the duty cycle of this kind of event, and argue that it lasts about 250 million years, then you find, and they argue in this paper, that these events should be happening every billion years or so for all nearby star-forming galaxies. So it gives us a constraint on the amount of inflow and frequency of inflow events experienced by nearby spirals. Another really cool way that H2 region abundances can tell us about how gas falls into galaxies is from measurements of the metallicity of extraplanar H2 regions. And there are not too many measurements of this, but Chris Hauk has done some really cool work. He has studied this extraplanar H2 region above the disk, about 860 parsecs above the disk of the nearby Edge-on galaxy, NGC 4013. And by looking at emission line ratios, comparing emission line ratios between this object and H2 regions in the disk, they find that its metal content is about half that of the disk. And they argue that it cannot be purely ejected disk gas given that differential. They also argue that because this object is relatively close to the center of this galaxy, it's unlikely the formation of this H2 region was triggered by a minor or major merger. Instead, they argue that it is consistent with the condensation picture, that the formation of this region was triggered by galactic fountain material causing condensation of hot coronal material. Now, interestingly, this implies that, if you start with a corona that is completely pristine, this H2 region must have been composed of half coronal material and half ejected material, which is a pretty high fraction of coronal material in the context of these condensation models, and they discuss that in the paper. That might be an interesting thing for us to discuss as a group. In this paper, they also helpfully collect the other measurements of extraplanar H2 region metallicities. There are very few. They are collected here, represented here on this diagram at the right. And this is height above the disk for these regions. And then they're basically showing here, this is the metallicity gradient. They're showing here that basically all of the other extraplanar H2 regions have a metallicity very similar to that of their host disks. So this one above NGC 4013 is kind of a low metallicity outlier. So that concludes what I wanted to say about inferences we can draw from H2 region abundances. I'm going to try to move this Zoom thing. Okay, so we find from characterization of anomalously low metallicity regions evidence for episodic inflow events happening maybe once per gigayear in star-forming galaxies, and also some evidence from extraplanar H2 region abundance measurements of condensation-triggered condensation of coronal gas. Any questions so far? Okay. I will continue. Let's now turn to insights we can glean from studies of H1 and 21 centimeter emission. Now, this is probably a pretty uncontroversial statement. We know the rate of inflow onto our own galaxy, the best of any galaxy. And in the review article led by Mary, which she talked a bit about in her keynote, she develops a model that she uses to calculate the inflow rate of high velocity clouds onto the Milky Way. And to do that, she first of all includes the high velocity clouds with well-constrained distances only, and then models the motions of these clouds with a single azimuthal velocity and a single radial velocity. So that's velocity toward the galactic center. And so if you force all of these clouds to have a single azimuthal and single radial velocity, then you find best fit values for those velocities of 77 kilometers per second and negative 40 kilometers per second. So, which is implying that as a collective, these objects are falling inward toward the disk at about 40 kilometers per second. Now, she's also put together a plot showing the total mass that will be accreted onto the Milky Way's disk as a function of time due to the infall of these structures. So here, she's just assuming that the inflow velocity of all of these objects remains constant as they move toward the disk. And she's showing us here when each of them will hit the disk, and then mapping the total accreted mass over time on the y-axis. The slope of this relation is then the mass accretion rate, and she finds an accretion rate of less than 0.1 solar masses per year, assuming this best fit value of the inflow velocity. If she instead assumes a much higher velocity of 200 kilometers per second, kind of the highest velocity allowed by the data, then she measures a maximal accretion rate, what she calls a maximal accretion rate of 0.4 solar masses per year. These values assume some correction, I believe, for the ionized fraction of these clouds, but to include a full ionized accounting of the ionized component of these clouds, you want to multiply these numbers by 2. So the maximal accretion rate onto the Milky Way then would end up being about 1 solar mass per year. So That's the high velocity clouds. Of course, there are also the intermediate velocity clouds, perhaps my personal favorite kind of cloud. The Milky Way intermediate velocity clouds have lower velocities, so less than 100 kilometers per second. They are quite dusty, they're metal rich, they are biased toward negative velocities, and so are likely in falling, and they stay close to the disk at heights less than about 2 or 3 kiloparsecs. And Phil Richter, in a review from a couple years ago, estimates the neutral gas accretion rate of intermediate velocity clouds. It's quite a bit lower than that in the high velocity clouds. This is just the neutral component of the IBCs, but it is only 0.01 to 0.05 solar masses per year. All right, so that's the Milky Way. We have quite good, relatively speaking, estimates of inflow rate onto the Milky Way. Now, we can also, in the Milky Way, we have the advantage that we can look very closely at the morphologies of some of these clouds. And from those morphologies, we can start to see exactly what happens when a cloud falls onto the Milky Way's disk. So one great example of this is the Smith cloud. This is from work by J. Lockman in 2008. The Smith cloud is a high velocity cloud. It has a mass of 1 million solar masses approximately, and it has a morphology. Here it is, and here is the gas in the inner Milky Way. It has a morphology that strongly suggests it is about to collide with the Milky Way's disk. It's about 7 kiloparsecs from the galactic center, 3 kiloparsecs below the galactic plane, and from its resolved kinematics, they can tell that this cloud is moving toward the plane at about 73 kilometers per second. And if you make a cut along the major axis of the cloud and plot the velocity as a function of a major axis, you get this plot over here. So this is major axis position versus H1 21 centimeter emission velocity. And this side of the major axis, or this point on the major axis, corresponds to these positions down here in this diagram. So the disk of the Milky Way is this black stuff here. And then he's showing portions of this cloud which are decelerating as they approach the disk. So he's identified clumps that look like they were taken out of the main body of the cloud and have slowed down as they approach the disk. So we see a cloud that's breaking up as it falls into the main body of the Milky Way. Another much more recent example of very high resolution H1 imaging of a high velocity cloud comes from Kat Barger, who imaged complex A. That has a mass of about 2 million solar masses, and its kinematics indicate that it is also decelerating toward as it approaches the Milky Way's disk. So they find that the velocity of the leading part of the cloud is lower than the velocity of the trailing part of the cloud. So it does seem to be decelerating as it approaches. It's moving in this direction. The Milky Way is in this direction. And they make the argument that this cloud must be sitting on top of lower density coronal material. So if the Milky Way is in this direction, then the gas over here must be much lower density than the gas in the cloud itself. And so they argue that this cloud should be developing Rayleigh-Taylor instabilities on this side. And they identify several morphological features which they liken to Rayleigh-Taylor globules. So that's what they're pointing out here as being features labeled RT. And these, so these are, these large structures that seem to be growing off the main body of the cloud. These RPS features are ram pressure stripped features. And then on the back side of the cloud, they identify more structures which could arise from hydrodynamical instabilities and which they liken to Kelvin-Helmholtz features. They don't have a way to quantitatively differentiate between Kelvin-Helmholtz or Rayleigh-Taylor features, but they identify these instabilities all across the morphology of the cloud, which I thought was really cool. Okay, so that's Milky Way H1. We get a really good global estimate of the inflow rate onto the Milky Way from H1 studies, and also a really detailed look at how gas looks as it flows and as it approaches the Milky Way's disk. Now, let's turn to what we can learn about inflows onto external galaxies by looking at H1 in emission. Excuse me. All right, so we've now known for quite some time from H1 surveys of external galaxies that extraplanar H1 is really common and that its rotation lags that of the disk. So this is just one demonstration of this effect. This is an H1 21 centimeter emission map of NGC 3198. And this is the major axis here. This is the minor axis. And so on the right-hand side, Marasco is showing us the H1 velocity along the major axis here. So this is direction or distance along the major axis. This shows the velocity profile of the gas along the major axis. The portion of the profile marked in white represents the gas that is part of the disk rotating along with the disk. But the part of the emission that's shown in blue, in light and dark blue here, is gas that is rotating slower than that of the disk. This is the lagging extraplanar gas. And this is a really common feature of H1 studies of other nearby spiral galaxies. So in this paper, Marasco et al., they develop a pretty simple model for to explain these H1 rotation curves. In their model, they have a regularly rotating thin disk and then a lagging extraplanar gas layer. And so to fit the data, they can vary the gradient in the azimuthal velocity of this layer. They can vary the radial velocity, so they do allow for the gas to flow toward the center or toward the minor axis of the galaxy. And then finally, they allow for an inward or outward flow component of this gas. And so they can vary these parameters, match to the data, and they find that, and here are the best fit parameters of that modeling. They find that the best fit parameters for the vertical velocity component tend to be 20 to 30 kilometers per second. So that's kind of the most important takeaway from this plot. They find that under the assumption that these extraplanar layers are axisymmetric, first of all, and smooth, and are well modeled by a single vertical velocity, that velocity is an inflow toward the disk of 20 to 30 kilometers per second. And they, in addition, are able to measure the mass in those extraplanar layers. That mass quantity is represented here. And they find that it is, interestingly, loosely correlated with the galaxy's star formation rate. So, from studies of H1, in 21 centimeter emission, we get great constraints on the inflow rate onto the Milky Way, and we find from kinematic modeling, or Marasco et al., I should say, finds from kinematic modeling that neutral extraplanar gas layers seem to be inflowing overall with velocities of 20 to 30 kilometers per second. Okay. So that's emission. Now, let's finally talk a little bit about absorption. Do I have 15 more minutes? Is that what I have? Okay, great. Thanks. All right, so now we're zooming out a lot. We're going to start talking about much more distant galaxies, and we're going to start to have a lot less information about the motions of the gas in these galaxies. We're doing a totally different experiment now. We're using the stars in the galaxies as a background light source. We're taking their spectrum, and then we're going to be able to probe the motions of any gas along the line of sight in absorption. So gas that's flowing out of the galaxies, of course, as you know, is going to give rise to blue shifted absorption lines. And by the same token, gas that's flowing back in towards these galaxies, stars, is going to give rise to red-shifted absorption lines. So these red-shifted absorption lines are what we're going to be looking for. Now, you already know it's really rare to see red-shifted absorption lines because of all of the outflow that galaxies are exhibiting. But it does depend somewhat on what kinds of galaxies you're looking at. So if you're just targeting starburst galaxies, which is what many early outflow studies did, then those are really going to be dominated by outflows. At the same time, you also really need to be able to have high enough signal-to-noise spectroscopy of individual galaxies in order to be able to see galaxies with inflow. And it took us a while to be able to have that, collect that kind of high-quality spectra. But it has now been done, and one of the first groups to do that was led by Taro Sato. who was analyzing quite high signal-to-noise spectroscopy of galaxies selected from the Deep 2 redshift survey at around redshift 0.3. And the spectroscopy covered the sodium 1D transition, which probes quite cold, dusty gas at temperatures less than 1,000 Kelvin or so. So this color magnitude diagram shows the distribution of their sample. You can see they have many star-forming galaxies, blue cloud galaxies in their sample, and also quite a number of early type red sequence galaxies. And the galaxies that are marked in blue here have detected outflows. So you can see they predominate in the sample. The galaxies marked in red have inflows. So this is red-shifted sodium. This is detected in 31 of their 205 objects and primarily occur on the red sequence. So this is a 20% detection rate, and they discuss how these galaxies, they don't seem to be forming stars, but they do have signs of nuclear activity, Liner-like line ratios or Seifert-like line ratios. And so perhaps these inflows have some connection to that nuclear activity. This type of redshifted sodium absorption has also been detected in a small fraction of Sloan early type galaxies. So this result by Sarzi et al. Kind of backs up this earlier discovery. So this was the first work really to identify outflows in a large sample of distant galaxies. It was followed pretty quickly by a study by Krug et al., who was studying sodium in Seifert galaxies, a sample of nearby Seifert galaxies, with relatively low star formation rates. And again, found a relatively high detection rate of redshifted sodium toward these galaxies of about 40%. And they estimate a very rough mass inflow rate onto these galaxies of between 1 and 5 solar masses per year. And that requires a lot of assumptions about the metallicity and ionization state of the gas, of course. And there are other examples, too, of inflows detected in transitions that trace quite cold material, such as OH, molecular material. And this has been studied in a sample of nearby X-ray selected AGN. So we do see some substantial evidence of inflow toward AGN host galaxies in general. When it comes to star-forming galaxies, we started to make progress once we were able to obtain high signal-to-noise ultraviolet spectroscopy of individual galaxies. And so we were able to probe the kinematics of magnesium-2 and iron-2 absorption, which are in the near UV at 2600 and 2800 angstroms in the rest frame. And so there are two works that made progress on this. One I led. This was part of a survey for winds traced by these transitions in a sample of about 100 galaxies at redshift 0.5. This diagram shows the star formation rate, stellar mass distribution of the target sample. You can see we detected a lot of winds. The galaxies where we detected winds are in blue. Galaxies without winds or inflows are in black, these black circles. And then galaxies, the 6 galaxies where we detected inflow, are shown in red here. So we detect, this is a detection rate of inflow of 6%. Crystal Martin has also done a sensitive Keck-Elreth study for winds in galaxies at redshift 1. Her sample was a bit bigger, 200 galaxies, but again, has a pretty similar detection rate of inflow of 9 out of 200 systems. So we have similar detection rates of about 5% in both of these samples. Now, we also noted that, there are only 6 of these galaxies. We have nice HST imaging of these galaxies. And we found that, they tend to appear in an edge-on orientation. So here I'm showing the distribution of inclinations for different subsamples. Galaxies with winds are shown with this blue line. They tend to be more face-on, whereas galaxies with inflows are shown in this red histogram. They tend to be more edge-on, although, of course, it's only 6 galaxies. But I do think that we are seeing here some evidence for, this blue stream. And, but at the same time, our failure to detect inflow in face-on galaxies does not mean it's not there. You could easily hide inflows of 100 kilometers per second in the line profiles that we observe, even for galaxies where we detect outflows. And we tried to demonstrate this in our paper. For example, here's a magnesium-2 profile for a galaxy with an inflow. We say it has an inflow because it has a lot of equivalent width redward of the systemic velocity here. So that's why we detect redshifted absorption in this system. But here are some examples of line profiles where we detect outflow, and you can see they also have significant absorption redward of systemic velocity, similar to that in the inflow profile. So these galaxies with detected outflows could easily be hosting inflows that are just at a bit lower velocity. Okay, so that's what we can learn by simply increasing the signal to noise of our spectroscopy. Increasing our spatial resolution also can help quite a bit. And this was done by Mark Westmaket several years ago now. He took WIN IFU spectroscopy of M82's star-forming disk and studied the H-alpha kinematics along the major axis of M82's disk, as well as sodium-1 absorption kinematics along the disk. And so you can see this is distance from the minor axis, so distance along the major axis versus radial velocity. And you can see the overall rotation of the galaxy here, traced by the H-alpha in black, but you can also see that there is a component of sodium absorption that is counter-rotating, this green component here, which is suggestive that it's due to some recent accretion event, some recently accreted clump of gas, likely along the major axis of this galaxy. Counter-rotating sodium. There you go. All right. So we're discovering perhaps signs of inflow in, the canonical outflow galaxy M82. And clearly the flows are happening at the same time. Some other interesting, very recent work on this was done with the new Megara IFU on the GTC. And they were targeting this galaxy, this edge-on spiral, UGC 10205. And here you can see the continuum image from their IFU observations. This instrument is really interesting because it has quite high spectral resolution in addition to spatial resolution. And they end up, with that spectral resolution, they end up detecting multiple components of sodium absorption across this galaxy. And in fact, they detect what appears to be an inflowing shell of gas with a velocity of about 100 kilometers per second, positive 100 kilometers per second, all the way across their field of view. And so you can see that here, they're extracting data from this area of the IFU. They see this redshifted sodium component. And then here, when they study this region, extract this region from the IFU, they uncover multiple components of sodium absorption, both outflowing and inflowing. So they're able to detect these things happening at the same time. Some other work on this was done without any IFU. It was led by Yang Zheng, and she did the hard work of spatially resolving the gas flows across M33 by simply observing star clusters across the disk of M33. And I wish I were not running out of time. So I'm sorry, I'm going to try to speed up here, Yang. You don't deserve this, but she finds that the absorption probed by silicon-4 is generically redshifted toward, measured toward all of these sightlines, and you can see that absorption, those absorption profiles down here. And they model the accretion that's exhibited by these line profiles and find a best fit accretion velocity of 100 kilometers per second or so. And they measure quite a robust mass inflow rate of about 3 solar masses per year towards this galaxy. Now, if we want to improve our statistics, we can turn again to the MANGA survey, which again probed or has taken IFU spectroscopy of a sample of 10,000 nearby galaxies. It covers sodium, the sodium transition in these galaxies. And so while it does not have spectacular spatial resolution or spectral resolution, it can help to give us some sense of how frequent inflows and outflows are across the surfaces of these galaxies. And so this is analysis that I've been pursuing for a while, and I won't step through all of these details, but I'll give you the upshot of what we seem to be finding. We're sensitive to flows with velocities of at least 55 kilometers per second. So that's when we think we can measure inflow robustly towards the surfaces of these galaxies. And we find that, instances of isolated inflow toward these galaxies about 15 to 20% of the time. We also see that these inflows tend to be more frequent in more face-on, higher star formation rate galaxies. And I'm happy to speak more about this if people are interested. So, To sum up our results on absorption line studies, we've seen quite a bit of evidence that inflows of cold gas traced by sodium are quite common in early type galaxies and Seyfert AGN host galaxies. Inflows of low ionization metals arise in 5 to 10%, at least 5 to 10% of star-forming galaxies at redshift 1. Don't forget about the inflow toward M33 that Yang discovered. This is a star-forming galaxy, but its disk seems to be completely covered by an accreting layer. Spatially resolved spectroscopy often reveals, when we have it, simultaneous outflow and inflow in both edge-on and face-on galaxies. And this is a reference I knew I wasn't going to have time to talk about, but this also studies by Stephanie Ho and Crystal Martin have also been really important for showing us how gas inflows towards galaxies along their major axis. So definitely check out this reference. And I will end by returning to these two models. I think I'm going to just say here that I think we have evidence for all of the aspects of inflow that are predicted in these models, both condensing inflow triggered by galactic fountain activity and gas that is accreted along the major axis from larger scales. But I'm happy to, discuss the issue. I look forward to it. And that's it. Thank you.
Thank you very much. That was a beautiful talk. And I will, it's right now 4 minutes after the hour. And I will quickly share my screen so that I can post some corrections. I need to apologize to Fariz Zahedi for not remembering that contribution number 4 in week 5 new results is his. And also I messed up on the panelists. I mixed up Thursday and Tuesday panelists. Here are the actual panelists. And how about we can reconvene, do we want to do 10 after the hour? So that gives a 4.5 minute breather. Okay, so I'll have a 4.5 minute breather and then reconvene for the panels. And I'll ask the panelists to be perusing the Slack because there are a lot of questions and interesting points that are raised there. And so when we pose questions to the panelists, our primary method of doing that is through the Slack. So please, while you're taking your break, take a look there too. Thank you.